Hello, it's Scott Manley here. I've talked about the rocket science of The Expanse in the past. In that show, the fusion drives are a rare thing for science fiction in that they're actually sort of within the laws of physics, albeit likely beyond any technology that could be developed soon or possibly ever. In the TV show, the spacecraft have engines that are able to provide powerful thrust comparable to the chemical rockets that we use to launch rockets into space, but they're able to operate for days or even weeks at a time, like the ultra-high efficiency ion propulsion systems used on deep space probes today. It would be really nice if there were something that we could imagine in real life that could do both, right? And there are smart people that have come up with a few ideas over the years. So I want to talk about one particular thing known as the nuclear saltwater rocket. And it's the brainchild of Robert Zubrin. And you might have heard of him because he is the sort of guy behind the Mars Direct concept, which has sort of become the basis for most of the plans to send humans to the Red Planet. So, rocket engines, they obviously work by sending out exhaust, reaction mass at high velocities in one direction, and the conservation of momentum means that you get thrust in the opposite direction. And they need a lot of energy to throw out the material. In conventional chemical engines, the combustion of the fuel provides the bulk of the energy. Whereas in ion thrusters, that energy comes from solar panels that are soaking up the sun. So the power from those solar panels is actually pretty wimpy compared to the fury of a chemical reaction, but both of them are much lower energy density than what's available from nuclear reactions. Now, there are actually nuclear thermal engines, and that's where you have a nuclear reactor and you blow propellant over it to cool it down. And so that you can heat the propellant to a relatively high temperature and use the reactor sort of continuously with a lot of propellant. Now, this may sound crazy, but they've actually built and tested these in the past. In fact, they did a lot of testing in a place known as Jackass Flats. The program to develop these was shut down, probably because it was a key step to potentially extending the Apollo program to Mars, and government really wasn't wanting to fund something as extravagant as that. So anyway, nuclear thermal thrusters, they're about twice as efficient as the best chemical engines. But there are limits on this, because to make things better, the reactor needs to be hotter and hotter. But if it gets too hot, then it'll melt. I mean, it won't melt down because it's in 0G, but having a liquid or even vaporized core is not good. I mean, it sounds catastrophic, right? But there are actually ideas for gas core nuclear reactors where the reactor is actually a superheated plasma containing, fissile uranium or plutonium. This is obviously a technical challenge, but that's a whole other video. No, the nuclear saltwater rocket works by having a sustained nuclear reaction in the propellant as it flows through the engine itself. It's just like a chemical rocket, which has a chemical reaction as the fuel flows through it, but with vastly more energy available to it. The exhaust from a chemical rocket is thousands of degrees, but it could be hundreds of thousands of degrees in a nuclear saltwater rocket. So, the propellant is water with a uranium or plutonium salt dissolved in it. The original proposal had a 2% uranium tetrabromide mixture with regular water. The uranium itself would also be enriched to about 20% uranium-235. That's reactor-grade uranium. So in that mixture, it contains everything it needs to sustain a chain reaction. If you get enough of it in the right place, you will have a critical mass and the neutron-driven reaction will run away exponentially and the water will explode into hot plasma. So the first problem is making a fuel tank that can store huge quantities of propellant. And you do this by having a lot of neutron-absorbing materials spread throughout the interior of the tank. Things like boron, which will soak up those excess neutrons before they can drive a runaway reaction and ruin your day. If you have a fuel leak, by the way, then you better hope that it doesn't accumulate in any one place. Otherwise, it will eventually react when it collects a critical mass. So the neutron suppression is a key part of the fuel handling, and that has to be maintained right up to the point where you actually want it to react. So in simple terms, you pump the salt water down boron-lined pipes into the chamber, and if you do it at the right speed, you can get a highly energetic, self-sustaining nuclear reaction which generates incredibly energetic plasma, and it's this plasma which generates the thrust. This isn't like the slow chain reaction you get in a regular nuclear reactor where it's only barely critical so that they can control it. This is a reaction where the criticality is maximized to burn as much fuel as possible before it expands into space. It's kind of like trying to replicate the prompt criticality conditions in the excursion that destroyed the Chernobyl reactor, but then you keep it running at that level continuously. Sounds fun, doesn't it, eh? So yeah, the water is of course key to this whole process. Uranium at 20% enrichment doesn't undergo a chain reaction on its own because the highly energetic neutrons that come out of those fission events have a very low probability of triggering another fission event. But slower neutrons are much more likely to make further fissions possible. So the water basically acts as a moderator. Those highly energetic neutrons, they freshly liberated from a fission event, bounce around off the water molecules until they're moving around slowly enough that they can make more reactions happen and sustain your reaction. And this bouncing around leads to another trick that's in play in the design. So you want to keep this highly energetic reaction under control because, of course, the neutrons are bouncing around in the water. They actually get dragged along by the water flow, right? They're bouncing off the water molecules and that takes time, and so they end up getting pushed along. So if the water flow is fast enough, you can actually stop the neutrons running upstream into the rest of your engine, which is probably a good thing because you don't want a nuclear reaction running up inside your engine plumbing where you don't want nuclear reactions to occur. Depending upon how you do the math, you need to get the water moving maybe at around 66 meters per second. It could be higher depending upon how you do your math, but this is something that's sort of doable. It's not like supersonic water flows. Of course, that's about 240 kilometers per hour for those that are keeping track. But yeah, do that and the majority of the reaction will stay happening in the place where you want it to. So there's another way to think about this, and that is as a continuous thrust version of the Orion nuclear pulse drive. That's where you take nuclear bombs and you set them off close to a pusher plate and that pushes the spaceship along. But instead, you've got a continuous nuclear explosion happening. So to generate thrust effectively, you need to direct all this fire and fury. All these exploding gases need to be directed using a nozzle. But with the amount of heat and radiation, any unprotected physical nozzle would vaporize in short order. So the design has a layer of regular clean water running around the outside, and that acts as an insulating layer, protecting both the nozzle from the heat and the radiation. So, some numbers. The paper estimates that perhaps you'd only have 0.1% of the uranium-235 undergoing fission, which at 2% concentration salt, 20% enrichment, gives you 3.4 gigajoules per kilogram. That's about 900 times the energy density of TNT. And that translates to an exhaust velocity of about 60 to 70 kilometers per second, depending upon how good your nozzle is. That's about the same as the exhaust velocity from ion thrusters. But in this case, you're no longer limited by the tiny amount of power that you can soak up through those solar panels. So the sample design that was in the paper, it used an inlet pipe which was 6 centimeters in diameter, like that size, with a propellant flow of 200 kilograms per second through that, and this would generate a thrust of about 1,300 tons. That works out to a steady state power of 700 gigawatts, which, by the way, when Chernobyl reached peak power during its explosion, it was about 350 gigawatts for a fraction of a second. This is 700 gigawatts continuously, right? It's a non-stop Chernobyl going on. Now that thrust is roughly equivalent to 2 F1 engines that they used on the Saturn V. those, of course, to do that, each required 2.5 tons of propellant. So if you only need 200 kilograms versus 5 tons, that's about 25 times more efficient, which is a nice step up. To be clear, you really wouldn't want to use this as the first stage to a rocket on the ground. It would spread nasty radioactive fission products all over the place. It would make the Rocky Flats nuclear facility cleanup look, well, easy in comparison. But in deep space, that radioactive exhaust is going so fast that it rapidly spreads throughout space and goes to almost zero concentrations. In fact, some of it is going so fast it will leave the solar system altogether. Now, if you were to say, look at SpaceX's Starship and then build a version with a nuclear saltwater rocket, same amount of propellant mass. Starship right now, in theory, gets about 8 to 9 kilometers per second of delta V. You switch it up with a nuclear saltwater rocket, you could get 150 kilometers per second. You could travel to Jupiter in a couple of months and come back in a couple of months using, single fuel load. It's quite amazing. To people thinking about the future of space, futurists and science fiction writers, the nuclear saltwater rocket is actually pretty attractive because there's nothing fundamentally about it that breaks the laws of physics. There's no obvious showstoppers that a bright student can point out. Sure, the simplistic sketch in the paper would likely to have a lot more complexity if it was turned into a real engine. You'd probably need neutron sources and neutron absorbers near the injection point that you could reconfigure to control the reaction. And, while pumping fluids at this rate isn't too hard, there's a question of maybe how you would power those pumps without adding lots of excess mass. But these are easy problems that we can think of. Indeed, it's entirely likely that there's fundamental parts of material science that simply can't deliver the kind of properties that we would need to turn a theoretical possibility like this into an engineering reality. But just say it could be made to work. Then the same paper did the math for a more powerful, more efficient version. Instead of using reactor-grade uranium, it used weapons-grade uranium, enriched to 90% uranium-235. And then it assumed more of the uranium undergoes fission. And in that case, something like this would have an exhaust velocity possibly over 1% of the speed of light. And then you'd be in the position to send spacecraft to other stars in decades rather than centuries. So, even if science delivers the ability to fly around the solar system in a few months by riding a continuous nuclear explosion, we'll still be able to dream of a sci-fi future where the ships could go faster still. I'm Scott Manley. Fly safe.